A warm welcome to the 38th session in the second module of the course Signals and Systems. In the previous session, we had been looking at a very important theorem called Parsifal's theorem, which essentially equates the inner product with signal representations in two different domains. In fact, the Parsifal's theorem is profound, a deep result in its own right. Although the way we looked at it, it derived from the multiplication theorem, it has a very deep meaning on its own. Let us look at what the Parsifal's theorem says specifically in the context of the Fourier transform, and let us also interpret it once again and bring to our own notice the depth and the importance in that result. So, we have talked about Parsifal's theorem last time in the Fourier domain, and what the Parsifal's theorem said really was that if you looked at integral minus to plus infinity x t y bar t dt, it was equal to 1 by 2 pi integral minus to plus infinity capital X omega capital Y omega bar d omega, given that x t and y t both had Fourier transforms and their Fourier transforms were x omega and y omega. Now, we had interpreted this as a consequence of inner product. So, we noted that integral minus to plus infinity x t y bar t dt is an inner product using a time domain representation. X t is a combination of impulses, unit impulses, and so is y t. So, what we really meant was that you could think of these, x lambda and y lambda as the components, and you could think of these, the delta t minus lambda, as the orthogonal basis. Now, in this particular case, the orthogonality is trivial, because if you look at any two impulses which do not coincide, they are non-overlapping. So, their inner product is trivially 0. Though of course, I must caution you that inner products of impulses need to be understood by looking at the limiting situation. So, you start from a little narrow pulse and assume that if the impulses are not at the same point, the pulses are also away from one another, and as you narrow the pulses, their overlap goes to 0. So, in that sense, you should think of two impulses which are non-coincidental, that means they do not come to the same point, as being perpendicular or orthogonal. And it is the unit impulse, the unit part of the impulse, which also makes the basis orthonormal in a more general sense. See, I must caution you that I am trying to use certain intuitive explanations based on a vector perspective to make it easier to understand and appreciate the results that we have in the Fourier transform. But I am not being terribly rigorous. If an expert in functional analysis or real analysis were to listen to this exposition, he or she would sometimes be dissatisfied at my lack of rigor, but that is intentional. I wish to make it as intuitive as I can without sacrificing on correctness. So, at these points when I am saying that impulses are orthogonal, one must understand them intuitively, and then of course one can also make a more rigorous statement if one looks at books on functional analysis or real analysis, and that I would certainly encourage you to do if you are so inclined. It would give you a much more accurate insight. But right now our aim is to get an operational understanding with some level of intuitive appreciation of what is going on. So, this is a little background. I needed to explain this because I want to be cautious in telling you that I am not being perfect from a functional analytic or a real analytic sense. Anyway, with those remarks, two impulses located at different points are in that sense perpendicular because they are non-overlapping, trivially orthogonal. And let me once again review and give you a slightly different way of understanding that the e raised to the power j 2 pi f t's or e raised to the power j omega t's, whichever you like to call them, are also orthogonal. So, let us look at that too. So, I now continue to look at the specific interpretation of orthogonality of e raised to the power j omega t. Let us look at it from a slightly different perspective. You could begin with two different e raised to the power j omega t's, but spaced by a certain amount. So, let us consider the interval from minus capital T to plus capital T, and we take what we call the so called fundamental frequency, and we take frequency spaced by the fundamental frequency. 2 pi by 2t, 2t is the interval here. So, therefore, essentially we are talking about two different e raised to the power j omega t's, but spaced by this frequency spacing. So, we consider omega 1 equal to some multiple, let us say k times 2 pi by 2t, and omega 2 equal to L times the same quantity. And now it is meaningful to talk about the inner product of e raised to the power j omega 1 t and e raised to the power j omega 2 t restricted to the interval minus t to plus t, and that is going to be integral from minus t to plus t e raised to the power j omega 1 t e raised to the power j omega 2 t bar dt, which is very easy to evaluate. In fact, it is minus t to plus t e raised to the power j omega 1 minus omega 2 t dt. And of course, there are two possibilities here. Either we could have omega 1 equal to omega 2, in which case we just get a constant independent of k and L, let us do that, and if omega 1 is not equal to omega 2, in other words k is not equal to L, let us consider both the cases. So, let us look at this case. Now, here if omega 1 is equal to omega 2, of course, we are talking about the case k equal to L. If omega 1 is not equal to omega 2, we are talking about the case k not equal to L. So, we have the two cases k equal to L or omega 1 equal to omega 2 implies the inner product becomes simply minus t to plus t 1 dt, and that is 2t. And of course, when k is not equal to L or omega 1 is not equal to omega 2, then we have the inner product becoming e raised to the power j omega 1 minus omega 2 t divided by j omega 1 minus omega 2 evaluated from minus t to plus t, and that is very easy to evaluate. It is e raised to the power j omega 1 minus omega 2 into t minus e raised to the power minus j omega 1 minus omega 2 into t, the whole divided by j omega 1 minus omega 2. Note that omega 1 is not equal to omega 2. And of course, you can simplify this, because this is essentially a sine kind of quantity. So, we have this becomes 2j sine omega 1 minus omega 2 into t divided by j omega 1 minus omega 2, and you can multiply and divide by t. So, that gives you 2t sine omega 1 minus omega 2 into t divided by omega 1 minus omega 2 into t. Now, what is omega 1, what is sine omega 1 minus omega 2 into t? Let us evaluate it. It is k 2 pi by 2t minus L 2 pi by 2t into t. So, that is essentially k pi minus L pi. And since k is not equal to L, of course the sign argument sitting on each of them, and since k is not equal to L, this must be equal to 0. Anyway, even if k were equal to L, it would be 0, but then you could not have the denominator. So, very clearly, when k is not equal to L, we have orthogonality. Now, you will notice there is a slight difference in the way I am constructing the proof. Now, I am taking frequencies which are spaced by that fundamental spacing or fundamental frequency of 2 pi by 2t, and I take any two of these. I have got a general expression for the inner product, then I have substituted the specific values of the frequencies, and I find they are identically 0. These inner products are all identically 0 when k not equal to L. Now, let me draw this on the frequency axis. So, what have I said here? This is when k is not equal to L, and the spacing is frequency spacing, I mean 2 pi by 2t. So, let us now look at the frequency axis. What you are saying is, on the time axis, I took my interval to be minus t to plus t, this interval, 0 exactly in the middle. On the frequency or angular frequency axis, let me write it explicitly, this is time t, angular frequency axis. I have a spacing of 2 pi by 2t, and I am considering these frequencies which I am marking here, 0 being one of them, uniform spacing, and we are saying that these are all perpendicular frequencies, mutually orthogonal. Now, what happens as t grows to infinity? As t grows to infinity, this widens this way and this way. So, starts covering the whole real axis, covering all time, and the spacing goes smaller and smaller. However, this continues, this orthogonality continues, this mutual orthogonality continues. So, now we understand what is happening. As we take t towards infinity, you have frequencies coming closer and closer, and they are still mutually orthogonal. So, the bigger you make capital T, the more the set of orthogonal frequencies you get, and in the limit, of course, as you go all over the real axis, the entire angular frequency axis comprises of orthogonal components. So, on the other side of Parsifal's theorem, we have a set of orthogonal components which we have now identified. We will see more about this in the next session. Thank you.